Alright, so let's start. Um, so as I said before, we go into the tree phase. So this week or today, I'll just be going through the theory and stuff. During the week, I'll post a PDF with questions in the chat, so y'all can read. But once you'll understand the concepts here, the other stuff like the questions and thing will be fairly simple. All right. This topic, if I tell it, yeah, three things you must know is the configuration, which is basically how to draw it, the equations for each configuration, the power equation, which is the easiest thing, is the same for both configurations, and how to draw the phasor diagrams. Once you know how to do those, the questions are real simple. Trust me, it's not difficult, right? So I'll go and show you all probably like two levels higher than what you need to know right now, but it's the same concept. All right, so let me just disable this. All right, so let's go. Right, so we just zoom in on this. Right, I think I just talked about this stuff we wanted to go through. So let's start. All right. So y'all would have started this already. So the types of configurations, so the popular ones, we call them the star and delta, or Y and star, Y and delta. The delta one is the one that looks like this, and the star is the one that does look like a star. Yeah, if you hear Y is the same thing. So normally they'll call this the Y configuration, and this one the delta, or they might call this one the star. They're all in the same thing. If you forget it, the one that look like a star, that is the star, and obviously the other one, that is the D, the delta. Right? So sometimes this does look like a D, a slanted D. If you look at it long enough, and this obviously does look like a Y or a star, but those are the configuration, right? So three phase, right? So why they call it three phase? Think of each of these coils, we call these coils like transformers, right? Single phase transformers. So these are three single phase transformers here, right? And three of them together, normally, they are 120 degrees out of phase, which I'll show you just now in a diagram. So when all three of them it'll go into red, yellow, and blue line voltages. So that is what these lines on top here are. Right? So those are the lines, and these like the transformers, right? So that way they get the three phase systems from. But basically, there's three single phase transformers, and each transformer have a line. When you pull all three together, you get a three phase transformer, right? Or a three phase supply, whatever you want to call it, right? And you can connect those supplies in either the delta configuration or the star configuration, depending on what you want to do. Key thing you could watch is how in the star, it have a neutral line, right? But in delta, it has no ground or neutral line. So you probably notice that, right? This star have a neutral going. So it still have the red, yellow, and blue phase, but have a neutral for the star, and for the delta, it's just the red, yellow, and blue. So have no neutral line, right? Right, so first important thing, right? The phase sequence, right? So is determined by the occurrence of the maximum voltage. So any your questions and stuff, majority of the time will be a balance supply or a balance system, which means that the peak voltage for each phase is the same. Right? So remember for our waveform, right? Like if I make a normal sign, the on top here is V peak. Yeah. So this here for balance system, the peaks for each will be the same. Right? So if there is one phase, another phase might come like this, not drawn to scale, that's a sketch. Right? And then another phase will probably like starts. Yeah. So all there's three phases, the peaks are the same, assuming it's a balance system. If it's unbalanced, obviously one phase might be loaded more than the other phases, so the peaks will be different, right? But for normal questions with what you all will get, meaning that your load will be the same on each phase. So the peak voltage will be the same, right? It's a balance system, right? So first thing. Second thing, when you draw any phase, and this will come in handy when you draw any phase, right? There's a direction for each, right? So when you're looking at it counterclockwise, is normally taken as a positive direction. So there's something to remember, right? Very important, right? So therefore, after you get the reference line, I'll show you what the reference is. The reference is always at 0 degrees, right? Like we said, this is the first phase, right? So call this V1 for now, right? Because second thing to remember, each phase is 120 degrees away from each other. Yeah, the second thing to remember, right? So if this is the reference, V2 will be 120 degrees away from the reference, right? So we call this V2, right? And then this way, because counterclockwise is positive, this direction here will be minus 120 degrees. But this here, minus 120 degrees, right? They are 120 degrees away from each other, but depending on what direction you're going in, and you'll see this more when you try the phaser, if you go from the reference, if you go to V2, it'll be 120 degrees. But from the reference, if you go to, they call this V3, it'll be minus 120 degrees. All right, so three things to take away from this slide. The direction, anti-clockwise, is taken as a positive direction. Secondly, each phase is 120 degrees away from each other. That's like how this diagram says. All right, as remember those two, because it will come in handy, right? And well, it's important for three-phase motor since the rotation. Yeah. So if you're going in the anti-clockwise direction, positive, clockwise, negative. Remember that. Because it will come in handy when you're drawing your phasors. Right? So that's all you have to take away from this one. Right? Alright, so let's get into something. So the voltage and current relationship, right? So any questions that you all will get, all right? The three-phase voltage system comprises of the three single-phase generating voltage, right? Remember, it's just three single-phase generators connected, right? And each have a line, right? So they have the same amount, right? Meaning that the peak is the same, right? They have the same frequency, yeah, because they can have one to different frequencies, right? Because the supply that come into your homes is not different frequencies for each person. It's a flat frequency, yeah? Whether you're in South, Chaguanas, Central, it's still 60 hertz, right? All right, this is what I told you before, right? The voltages or current time displacement from each other is 120 degrees, right? So I told you all that already, okay? And the reference phase is 0. The reference, you could pick any phase to be the reference. It don't really matter. Yeah, but because it's a reference, you'll put that at 0 degrees. Yeah, it don't really matter what angle it's starting at. Once you know the reference, you just put that at 0 and you go ahead. It doesn't matter which one. But for you all, once you say you pick VA, because I know the better one to pick A, because it's the first one, put that at 0, and you know every other phase is just 120 degrees away from each other. And now you know when you're going in clockwise direction is minus, or when you're going in the anti-clockwise direction is positive. All right, so if you have this here, so I'll use the diagram so you can see, right? So this diagram here, so you see how it's 120 degrees away from each other, right? You don't know what this is as yet, so don't beat up yourself too much, right? The reference line, remember I told you about the reference line is E. Simply enough, our reference line, right? This is 0 degrees. Okay, so we have A, B, and C. Don't worry about the C and for now, I'll show you that just now, right? So if I'm looking at this one here, if I'm going in the anti-clockwise direction, right? That'll be positive. So this will just be VCN angle 120 degrees. Yeah. And if I want VBN, because I'm going in a clockwise direction, the angle will be minus 120. Or VCN, another way you could write this instead of 120, you could write it as minus 240. Why? Because if I go here, from here to here is minus 120. And then from here to here is another minus 120. But VCN from the reference line going in the minus direction, let's say going this way, it'll be minus 240. It doesn't matter which one you choose, you'll get the same answer. All right? Because it's direction you choose. Once you know anti-clockwise positive, clockwise negative, you can reach anything else. All right. Same thing with this one here. Instead of writing minus 120, could have just go this way, right? But the consensus is whatever direction you choose, just keep it constant. So if you record your angles in the clockwise direction, just record all of them in that same direction, right? You don't be jumping too much, right? And the consensus is really when you're drawing it up. So your VA, that's for understanding purposes, 0. Then VB is minus, and then normally VC, the right, it has 120. Yeah, that is normally we'll see in books and stuff, right? But you know this 120 here, you can write it as minus 240, right? It depends on the direction you're going. I can't stress that, Anti-clockwise is positive, clockwise, negative. The phases or the currents, depending on what configuration you're in, is 120 degrees away from each other, right? So this diagram is what I want to draw. So you notice that the magnitudes or the peak is a balanced system, right? So you see now the peak is the same for each phase, right? And it's a three-phase system, so the three single-phase transformers. And together they supply a three-phase supply, right? So this how will look, yeah, on a voltage time or voltage angle graph, right? All right, something to remember, and this will help you more with questions, is that if they give you the rated voltage, that is the line voltage. Yeah, so in a question, I might say given that the rated voltage is 240, just know that is a V line. And trust me, once you know that, once you have V line, everything is going to open up for you nice. But that's something to remember. If they give you a rated voltage, they by definition give you the line voltage. All right, so that was the introduction. That is the foundation. So again, so the actual configuration, right? So the angles. So the equations, right? The equations are specific to what configuration you're in. So once you know what configuration you're in, the equations are different. Yeah. So if you're in a star configuration, right? So if I draw up a star, remember the stars you want to look like what a star, right? That's probably the easiest one to look to see, right? So these are your three supplied, right? So this is your neutral. Yeah, neutral mean not yeah, so you're running a neutral to it, right? So you run it like that. Ground, right? So this on top here is VAN, right? This one at the bottom here is B, it'll be VBN, right? And this one here you could call this VCN. Yeah. So that is how you would draw the star configuration, right? These currents on top here, these are the line currents, right? Right, and the currents inside here is the I phase. All right, so how to look at it is that these pieces here, think of it as the individual transformers that are giving you a voltage. Yeah, they are separate from each other. Okay, so they each pushing out a current. Yeah, so let's remember. So for the AN, VAN, you're seeing that IP and I line, they are the same. Yeah, just looking at the diagram, you can clearly see that IP, I line is the same because they're not breaking at all. Each of these transformers are isolated from each other, they're different. So this pushing out a current, and that current is what this line will see. So for a star, your I line is your IP. It's the easiest thing to see because of this one line here connected to that line. You'll see the difference with the delta. Same thing for this line here. You have your I phase is equal to I line. Same thing for this one here, I phase is your I line. Yeah? Just looking at the diagram, you can just see it. Because the star is normally connected like that. It's no break or anything else. So your I phase is your I line, or I line is equal to your I phase for your star configuration. Right? And then your V line now. So if I was to connect a voltage across this diagram, or connect probably a load, right? A load have to connect in between two things, right? Two lines, right? So when you're connecting it, let's say connect a load here, right? Clearly you can see this load here is the sum of these two voltages here. Yeah, mathematically, just look at the diagram. You can see that this load seeing these two voltage or these two sources here, right? Just looking at it. So clearly you could see that your V phase and your V line is not the same. Just look at the diagram alone. When you see that now, you will get this equation. Your V line is root 3 of your V phase. Yeah? As once you see, see it in the diagram, the equation will pop up too. Alright, so your V line, the voltage across the lines is equal to root 3 of your phase voltage. Yeah, so something to remember. How I used to remember it is that because it's cyclically, see the current, there's always a root 3 relationship. So if your I line is equal to your I phase, therefore the root 3 will be for the V line. That's how I remember it. Just to keep life simple. So since I know I line is equal to I phase, therefore if I wanted the equation for the V line, it would just be the V line is equal to root 3 V phase. That's how I remember it. Yeah? And because I remember star, delta is just the opposite. So for the delta, I line will equal to root 3 I phase, and the voltage will be the same for the delta. Yeah? So that's real. This is probably the easiest thing to just remember. Remember, if you forget, just draw the sketch of it. Three single phase transformers, and it's a star, so that have a neutral point in the middle. Draw your lines coming out of each of them and draw your phase. Your phase coming out of each of these supplies. And you will clearly see that the I phase is on the same line as the I line. So I phase are equal to I line. And by default, because they do that, therefore V line will equal to root 3 V phase. If you're having trouble remembering equations for these, it will always start with the line. That's how I remember it, right? So if your I line is I phase. And if your what the voltage will be V line is equal to your root 3, the root 3, and a V phase. That's your start. That's by looking at the diagram, right? And delta now. Delta is want to look like so you can see a triangle if you want to, a triangle. So it will look like this. So you have a source, then you have a next source, then you have a next source. Oops, I'll draw that coming down soon. All right, so these are your three, right? So and I could draw more lines coming out. Yeah, so for this one here, for the delta, when you're looking at the diagram itself, the first connect a load, right? Across our line, you can clearly see. Look at this one. Compare this piece here, this dotted line here. Look at that compared to this one here. You can clearly see for the star, the V line is not equal to the V phase. But for the delta, you can clearly see that this load, the voltage I'd seen is only across one phase. Yeah, so clearly your V line is equal to your V phase for the delta configuration. Yeah, you can just look at it and see that. Right? And by default, your I line will equal to the root 3 relationship. Yeah, so you can clearly see what's going on. So this I line is equal to I phase for the star, therefore your V line will equal to your root 3 V phase. And for the delta, just by drawing the diagram of it, and you connect a load across, you clearly see that this voltage here is this voltage here. So your V line is equal to your V phase. And therefore, because of that, your I line is equal to the root 3 of your I phase. Yeah? And those are the four very important equations that you must know. If you don't, pressure any car. Here's the foundation of everything. You start on your delta equations for voltage and current. All right? So, and these are the diagrams right here. So I'll show you these here now. So we went through the star, all right? And you can clearly see the I line and the I phase, right? And look like a star, right? You see. So when they join up the phases for your star, there's VAN, right? VBN and VCN. Yeah, so this will be like there's a B and there's a C, right? So that is your phase voltages, right? So for the delta, The star is with respect to voltage, and the delta is with respect to currents. Yeah, so that is the catch with it, right? So the currents here, the delta is respect to your current values. All right, so if this is A and this B and this is here C, just by looking at the diagram, all of them are direct with respect to the loads. So make it easier there. So like you said, this was A, B, and C. So delta with respect to current, right? So this current here, call it IAB, right? And then let me say I have a current here, call that IBC. The next one, if you call that one here, you call that one ICA. Yeah, so those are your line currents. Right, so delta with respect to current we're drawing it by default, and the star with respect to your voltages. Yeah, so that's something cool you can remember. So when you're drawing up the star, remember this is your neutral point. So everything will be with respect to that neutral point. So it'll be VAN, VBN, and VCN. Yeah, and for the delta is respect to current. So when you're drawing up your current values now. So with respect to current, you're just looking at the currents that are flowing in the diagram itself, right? So if I was to replace these loads with supplies, starting in this diagram to give you the load side of it. So we just convert it to the supply side, right? So with these supplies, remember we have a load here, we have one here, IE. So we say that going this way, and this going this way, and this going this way, right? So when you look at the diagrams itself, this going out, this going to go this way, this going to go this way, and this going to go this way, this going to go this way, right? Because it's a circle when you're looking at it. Right? So, but don't worry yourself about this. When you go to the phasors, you'll see what these are. But for now, these are the configurations, and these are the equations with respect to the lines and the phases for each of them. All right, your star with respect to your voltages, and the delta with respect to your currents. All right, right. So again, to the phasor part, right? So, right. So the star configuration we start with, and just like I told you before, the reference angle or whatever phase you choose to be a reference is 0 degrees, right? Just remember that, right? So for the star, we know that the I line is equal to your I phase, right? And because it's a balanced supply, your peak voltages will be the same for each phase, right? So that what I say VA and VB and VC is equal to your V phase. Yeah, they all have the same phase voltage because they're balanced supply. All right, so just keep that in mind. For balance supply, all your phase voltages will be the same. The peak will be the same, right? So now we have a nice diagram that actually showing you the supply part, right? So I'm gonna break it down. So I'm gonna change the color. So these here are your transformers, the generator and our voltage. We know the voltages are 120 degrees out of phase from each other. Yeah, we know that from the theory before, right? So we have the neutral point here, and we have A, B, and C, just like how we drew it up before. So this here, this phase, remember these are your phases, right? These are your phases. Remember that. Forget about the line that coming out at the bottom. These are your phases. Yeah? So what in between there is a phase, right? This phase here is called the VAN. It's called VAN, right? A here, and this one here is VBN, right? And this one here is VCN. Notice it going out. Yeah, well, obviously, it had to go out because the voltage of the current will go out, right? So, and this one here going out, out. This is VAN, VCN, and VBN. You need to remember these things, right? So those are your phase voltages, right? So we know the phase voltage, it have a relationship between the phase and the line for the star, right? So if I want the line voltage, I need to connect. Think of it as you're connecting a load across lines. Yeah, you're connecting it across the lines. So these things here are your lines, right? So you can connect loads across those things, right? And we know the line and the phase is different due to the root relationship from the equation, right? And you can clearly see it here. So if I was to connect one between A and C, yeah, call that VCA, right? Which is this one here. from here to here is VCA, and you can clearly see that it's made up of two supplies. And we know that V line is root 3 of your V phase, right? So you clearly see it not the same. All right. So you might be looking at it, the arrow, right? So you don't have to draw it like that, you can just draw it going up. Whatever direction you choose, just keep it constant, right? So you can just draw it going up. I like to draw it going up, right? 'Cause it makes sense when it going up. All right. If it connected between the B and the C phase, you get VBC. Yeah, and that would make sense. And then if you connect it between the A and the B, you get VAB. All right. Looking at it, VBC plus VAB, all right, will give you the entire thing from here to here. Or you can say VBC plus your VCA will give you the entire one, right? But that is looking at the lines, right? So this is your star configuration. You really need to sit down and memorize these. So I'll show you the phases, the V phases. So you have three. So you have a VAN, you have a VBN, and you have VCN, right? And we don't have to worry about the current because I line is equal to I phase fast start. So you don't even have to worry about the current for those. All right? And putting it all together now, if I choose VAN as my reference, right? I know that the V phase or the V peak is the same, right? So instead of writing VAN all the time, I could just write VP, okay? Because it's the same thing. So I could say this is equal to VP angle 0 degrees. Because there's a reference, right? And then VBN will be VP angle minus 120. Remember I'll show you to draw it up. So there's A. So now you know this is VAN, right? And then you know this up here is VCN, and you know this is VBN. I'm draw that AN better. You can look at it. All right, so you'll know if this is 0 degrees, this here, because this is the positive direction, this will be 120. All right, and this here will be minus 120. But because we know VAN is equal to VBN is equal to VCN, which is equal to your VP, because it's a balanced supply, you could just use VP and done. Yeah? So that's where I got these from. And obviously, VP will be 120 degrees, right? So something cool to remember. You're looking at it here, and you can see it, all right? 120 degrees away from each other. Yeah, but with reference to the reference, VCN is 120 or minus 240, depending on what direction you go in, and VBN is minus 120 or positive 240, depending on what direction you go in. All right, so that is your start. So I'll show you the phase, which is the things in black. I'll show you the phase voltages, VAN, VBN, VCN, and I'll show you the lines. So you have VAB, all right, VBC, and VCA. Every line is confusing, look at this. That's VAB is your first one. Then from the B, you get your next one, VBC. And from the C, you get your next one, VCA. That's remember. If you're kind of feeling overwhelmed, just start with a VAB. That's your first line voltage. And once you're right there, you start with the B and you go to C. Remember, it's A, B, C. Yeah. So you start with A to B is one, then B to C, and then C will just go back to A. That's what we're looking at. So A, start at A to B is your first line voltage. And your second line is VBC. That's your other one. And then from the C, you have VC. You just put it all together. You will end at where you start with. Obviously, you start with A, you end with A. That's what I remember. So these are your line voltages. So you have three phases and you have three line voltages, which is how masters work. Yeah, so the takeaway from this star configuration here, so I'll show you the phases, VAN, VA, VBN. I'll show you the lines, VAB, VBC, VCA. I'll show you how to remember it. I'll show you the relationship here. I'll show you that 120 degrees away from each other and everything. And you know the I line is equal to I phase. So the lines, you have your IA line, which is this one here, because what we see it coming out of the A. You have your IB, that coming out of B. And you have your IC, that coming out of C. All right, that's for the star specifically. right? So that's the info which you need to know for this star configuration, right? This relationship here will hold for the delta because obviously the configuration is still connected to our balance supply, right? So you see it now. So let's try something. So this thing here looking like madness is okay. So VAB, right? So VAB is between the VA line and the VB line, right? Yeah. So if I was to add these two together, so let's say I wanted to actually calculate what VAB was, right? So VAB, remember, if you want the line, you know, is the sum of the two. So I'm gonna just draw it so you could see it clearly. Just look at that piece of look. You can clearly see mathematics wise that these two, if I add up these two, I will get this long one going between, right? Just looking at that look. So if I draw an equation for the VAB, which is your line voltage, your first one will be the VAN, right? Plus VNB. Where does NB came from? Remember, are going up, right? So VAN already in the direction that I'm going, right? Because you see that VBN in the opposite, right? So all you gotta do just flip it. If you flip it, you just get VNB. Yeah, that's all it is. And if you want to write mathematically, it's just minus VBN. Yeah, it's just going up. So if something going in the opposite direction, you just flip it. So this here will just end up being either minus VBN or the better way to write this is just plus VNB. That is the better way. But when you plot in the phasor, it's better to see this. It's easier to see that because you know that it's just the opposite of VBN, right? It is the better way. Mathematically, this is the same thing. It does the opposite of VBN, which is minus VBN, right? But when you plot in the phasors and do any calculation, it's just better just to end with the letters and keep it positive, all right? So VAN plus VNB, which is the inverse of this, so you end up with this now. VNB, so VNB plus VAN will give you a VAB, which is this here, right? So that's like I told you before, VAB, a VN, and if you invert the VNB, yeah, you'll get this, which is exactly what I showed you. All right, when you're plotting the phasors, you could stop at this. You don't really need to go any further, right? Because the phasors are sketchy. You don't need to be accurate with the values, right? Which you'll see just now, don't worry. So, right, so VAB, remember I told you that the VAB, all those things, you can just use the phases. So VAN is VP and VBN is VP. Remember VAN, that's like I told you before, VABN, VCN is equal to a V phase, right? Because it's a balance supply. Yeah, balance. So the voltage in each phase will be the same. All right, just remember that. All right. So you can replace with VP. So if you do another calculation now, you can say Vn is Vp angle 0. That's like I show you. Minus a Vp angle minus 120 degrees. Now you know where this came from. Because you know that B, if A here, B here, and C here, they're just minus 120, right? So that's what this came from, right? So minus 120, and you get this here. This is a level higher than what you need to know. You really need to know this in depth. But something cool that when you draw in the phasors, you realize is that the line and the phase, they have a 30 degree, the 30 degrees out of phase from each other. So if you actually put that in a calculator, so like if you choose VP to be like 10, if you want, it really matter what you choose. So like 10 phasor 0 minus 10 phasor minus 120, you'll actually get that it actually is the root relationship, but it's 30 degrees out of phase, right? But for you all really use this. If you're in next semester, when you're doing in semester 2, you will have to include these. But for now, you all just leave all that and you'll just write V line. This is V line, right? Is equal to root 3 V phase. Yeah, you all really have to worry about this at that level, right? But it's the same relationship. But when you plot in the phasor, just have to stop up here. You don't really need to go any further. Right? They're just doing it out take a seat. But next semester or the following semester, if I'm doing power in year 3, there's something cool to remember. Alright? So if still ask it in class, well, you can answer because you know what you do. And if you ask you why, just go on the board, draw the star and show the directions. When you add it up algebraically, you'll get this. Choosing VN to be the reference, and you know VBN is minus 120. Put it in a calculator and you actually get the relationship. Yeah, but anyway, so that is star. Right, and that is basically what I'll show you just now. Yeah, probably write like 10 times VN, VP angle 0, VBN, VP angle minus 120, and VCN is VP angle 120. All right, and that's like I told you before, each line is 30 degrees ahead of the face. But you don't have to worry about that right now. Right? So that was star. Right? So should I draw the I'll draw the phase or not? Alright, so let's draw the phase, alright? So you can probably try this while I do it, right? So I'll draw dots because our phase. And our phase you have two things. You have your magnitudes and you have your angles with respect to each other. Right? So first thing I will draw is if you're drawing it with star, you have to draw a phase voltages, right? So let's choose VAN as the reference. So I don't normally write it. All right, so we have VAN here, and then 120 degrees from that, you have your VCN, and then 120 degrees from VAN is your VBN. All right, and I like to write 0 degrees so I will know what's going on, right? So nice. So I have everything here labeled. So that is your phases, right? So let's write. So remember from your phases, this here have to have your phase voltage and your line voltage, right? So let me start with the first line voltage, this is VAB, right? So VAB, if we go back to the diagram, but that was VAN plus VNB, right? Yeah, so remember, if I go back to the top, you let the equation to show this, yeah, plus VNB. Remember, you don't need to flip it because that would just overcomplicate the drawing up. You don't need to be so mathematical, right? So if I'm breaking this down, VAN is already here, right? VNB is just the reverse of VBN, right? So I could just draw the dotted line. Yeah, and right there is VNB. I don't need to put minus VBN here. It'll just look weird. Yeah, that's why I don't like to use the minuses when I draw the phase. So just keep it at VNB. Yeah, it's the same thing mathematically, but keeping it positive will make drawing the phases easier because it always gonna be the reverse of it, literally. Like a straight line is always gonna be the opposite, right? So now we just draw it. Okay, there's a parallelogram, so this will be the same thing, right? So now VAB, just like angles and phases and stuff. If I add VAN and VNB, which is what the equation gave you, VAN plus VNB will give you a VAB. So what you have to do now is just draw a line to connect the two. So you're connecting this here with the middle piece. All right, so you just draw the line. Pow. The side that you have VAB, and if you want to make it look nice, you can just connect the parallel stuff. So this here parallel, and that is it. Right? So the first thing, you write the equation first, because that would tell you how we're gonna look, right? So VAB is just VAN plus VN, right? So VNB is just the reverse of VBN, so you just draw the dotted line up on top, right? So because we know this here, that means that parallel, so that from here is the same thing as VNB, right? And you just, because of that now, vectors, you just connect the two, and that is, if you want to, you could connect the top and the bottom. So another way, train you all the other ways that you could do it, because some people learn differently. Another way I just draw it is just use the equation to draw our scene, right? So VN is already there. And if I plus in VNB, VNB will just be this, right? And then from vectors, it will just be the connection between the two. So from here to your center, you have your VAB. Yeah, because I don't know, you draw it already, so you can just draw up the parallel pieces, right? So this here parallel to this piece here, and then the VAN parallel to the piece on top. So you can just draw the dotted line to it. And that is one line, right? and then repeat the same process with the others. So you have VBC. Yeah, that's like I show you. So AB and BC. So the same idea. So I go up and see how they get VBC now. So let's erase this so you could see clearly. So I erase this. Like, so you want VBC, right? So VBC is in between right here. So let's zoom it. Right, so VBC is this piece here. Right? So remember it going up, right? So it'll be VCN plus VNB. Yeah, so that's like the equation. So the equation, well, I break it down first, but it's the same. So from here, just looking at the equations. So you have VBC here. So if you look at the relationship, VAN or VAB is equal to VAN plus VNB. Just look at the relationship. We'll look at it, watch it. So I will just show you how to remember, right? So look at the pattern. This A here, right? This A starting here, right? Look at it, and the B and then seeing that? What in between? Connecting them, the end. Seeing that? Look at it. You're literally seeing it. This, once you're already line, you're literally telling you what the equation is one time. You gotta hot up your head. So if I have VBC, I'm gonna use the same relationship. So it'll be VBN plus, you know the C, 3NC. If I want VCA, same idea. So I have VCN plus VNE. Yeah, and that's how I remember. Yeah. So you don't have to pay too much about remembering. Just remember the little pattern. Once you have V line with the star VAB, you start with the A and with the B and the other N. And the thing in the middle is N, right? Because it's all the reference to the N, right? So yeah, let's write that down for the other piece, for the phase, all right? So we have VB now. So it'll be VBN plus VNC. All right, so now with that, use the green. So we have VBN already. So that's like I'll show you how to do it. You can just connect the lines. So from here you have VNC, which is going like this. Yeah, and obviously you're seeing same thing like before. VNC is the opposite of VCN. So let's draw the parallel to it one time. Yeah, and then there's the middle piece. That's like vectors. You just connect the two endpoints. How? So that was VBC. And obviously to make it look nice, you could just connect the other parallel piece. Yeah. And then VCN is the same idea. Just like I show you also so we had VBC, so VAB, VBC. The next one is VCA. Same pattern. So you have VCN plus VNA. Yeah. And you just do it like that. So I try it. So what color? I use black. So VCN already there first. And VNA, if I do it the other way. So VNA is just the opposite of here. So you just draw that going up there. Yeah, when you draw any opposites, try not to draw it too long, right? Okay, the longer you draw it, it will look weird. Just draw it short. Right? And therefore this piece here had to be parallel. Yeah, and it just gonna connect the two pieces there. So from here, just draw a line to it. And that is a VCA. And to make it look nicer, you just connect the parallel pieces together. Yeah, that is it. Yeah, that is your phase already. So you have your phases and you have your lines connected to the phaser. And that is how it does work. Once you draw the equation, you can plot the phaser. Right? And that is your phaser for your star configuration. Right? So that is all it is really. Nothing much to do with those. Right? So you have the equations and that is your phaser. You will be asked to draw this in your finals. So I will leave this how I draw it here. So when I send you the document, you have it. All right, so let's run along to the delta configuration, right? So as I said before, the delta with respect to currents. Yeah, so that's something to keep in mind, right? Star, when you do it, the phasor will be with respect to voltage. and for your delta is with respect to the currents. All right. So just like they did before, it's the same relationship. You don't have to worry about this. All right. So just the opposite. So for the star, it was out of phase by 30 degrees. It was shifted, but for the current, it would have be the opposite. It would have been minus 30 degrees, but don't worry about it. All right. So for a balanced system, right, it's have equal. That's like for the star, it's the same thing, right? But the difference between these here, so your IAB, your IBC, and your ICA, these are your phase currents. Yeah, so looking at it with this diagram, right? Don't worry with the load, they can always replace those with supplies, right? So don't worry about, so if I replace with the supplies, we could see, right? It's the same thing no matter what side you're on, just one taking and one receiving, right? So if those are your supplies, this supply here, current will go in here, up, so it'll be ICA, and this one here is IB, because it's had to go this direction, and this here is IBC, it had to go in this direction. All that is to say is that in the triangle, it going around. It don't really matter. Just going this way, then from here, going down, then from here, go in that direction. I was say it just go in a circle. Well, not really a circle, but it going in one direction, really. And not reversing too much. Yeah? So from this here, because it's delta is respect to currents, right? And the three phase currents, yeah, so this one here, that's like this is A, this B, and this C, just like your start. I'm not gonna change. But it have no neutral. Yeah, and we know for the delta, the voltages are the same, right? So therefore, the current is the thing that will change, right? So the three phase currents, yeah, the first one, IAB, and the same pattern for these apply. If you ever forget it, if you start with IAB, the other one is IBC, and then from IBC, you have ICA, right? And you just draw this on top as a phase, right? And those are your three phase currents. Just looking at the diagram. So look at it. There's something to look at it. You still have A, B, and C. But those represent the transformers A, B, and C. Now, for the delta, the change will now with respect to the current. So you have your IBA current between A and B, where you're coming from, where you're going. Then you have your IBC, you're coming from B going to C. And you have your ICA coming from C going to A. And those are your three phase currents. Okay, you can clearly see those lines are in the phase. Yeah, within the bounds of your transforms. It never went outside. Yeah. So obviously ABC, you have your IA line, your IB line, and your IC line. That's like before. Yeah, they're not gonna change. Right, so look at it. So in your phase, so we'll just cut this so you can see. Right, within that, there's your phase system. Everything here is your phase, right? Outside of that, if you connect a line to A, or this point here, the delta, it have three connecting points. You have your IA, you have your IC, and you have your IB. Yeah? So, nice. So I'm gonna do one more thing with this. I don't have to go through this, because this, I will do that when I do any question, right? But it's the same idea. The same thing with the 120 degrees out of phase. It's the same thing for the currents. It's just everything switched from being with respect to voltage because of the star to currents because of the delta. So it's the same relationship that you're going to be using. All right, so I'm going to do something here for you all now. So you can derive the equations for your line currents, right? So your line currents is IA, IB, and IC. All right, so looking at this, I'm going to just erase these things that you're wrong. All right, so you could get these directions by just using, sorry, a little bit of 1000, right? So you're just using Kirchhoff's current law, right? So all it says is that the sum, if this is a junction here, this dot, okay, have three of those in the delta configuration, right? So you have three. So that means you have three lines, right? So for IA, if I'm looking at this A point here, the sum of the currents going in must equal to the sum of the currents going out. So this IA going in, ICA going in, and IAB going out. Yeah, so therefore, if I write in the whole equation, IA, because IA going in, plus ICA, because that's going in also, is equal to the sum of the current leaving, which is IAB. Yeah, so making IA the subject of the formula, you will have IA is equal to IAB minus ICA. Yeah, and that is the first equation fit. All right, and with this one here, that is for IB, the same idea, right? So looking at the IB node, so you go down to the IB, use a different color. All right, so let's try IB now. So if you go down to the IB node or the B node itself, this one here, yeah, so we know this going in, IB going in. All right, so IB, so the sum of the currents going in is equal to the sum of the current leaving, right? So IB plus your IAB. So IB plus your IAB, because IAB going in also is equal to the sum of the current leaving, which is equal to IBC. Right? I'm making IB the subject of the formula. You have IB is equal to IBC minus IAB. Yeah, and that is the second one. Right, and the last one is the IC phase. So IC. So C is here, right? And the same idea, the sum of the current going in is equal to the sum of the currents leaving, right? So IC plus IBC, can go in and also, is equal to ICA for that leaving. Make IC the subject of the formula. So that's equal to ICA minus IBC. Right? And those are your three lines and the equations for that, which will come in handy when we plotting the phasors. Right? Yeah, so I'll show you the phase currents. I'll show you the line currents. All this thing here is basically telling you that the currents and the relationship between them, which you already know. All right, and just like before, with the voltage, because it's a balance system, a balance load, the phase currents will be the same. Just like before with the star, the phase voltages were the same, the delta, the phase currents are the same. Yeah, so that's something to remember. This, you'll understand this more when you try a question, but it's the same idea. Your voltages is your reference, so 0, 120, minus 120, sorry, and 120, and is ZL is your load. So for balance supply, the ZL will be the same for each. Yeah, the load on each phase will be the same. Okay, it balance. All right. So you don't worry about that too much at this point. Right? Nice. So if we plot in the delta, so same idea. So you draw a reference, you draw the dots. So let me say we use an IAB as the reference. So you have IAB coming out here. All right, and then you have 120 degrees from that. You have another one, which is ICA, and then 120 degrees from the reference is your IBC. So, yeah, that'll go, yes, 100 over. IBC. All right, so you have your phase currents. So now you have to add in the line current, right? So that's how we did before. We had to use our equation to do what we want, right? So IAB, right? So if we go back to the equation that we had formed, so if we want IA with respect to IB, so your three lines numbers IA, IB, and IC. All right, so if we start with the IA, let's go back up to the equation we had. So IA was IAB. So IAB minus ICA. Yeah. So from this equation here, how it's written, yes, that we will get from the current flow, but I don't like to use it like this because of the minus. I mean, if you're good in math, you can clearly see that ICA, it would just be this here. Kudos to you, but some people can't see that. So what you could do, if you do see it, just invert the minus and make it a plus. So if you're doing that, it would just be IA, would just equal to IAB plus IAC, right? And you can clearly see that if this is ICA, IAC will just be going in the opposite direction, right? Remember, I say don't draw that too long because it will kind of make it look weird, right? So now we have that. Draw this parallel to it right here. And IA, just like I told you before, just like before with the star, it will just connect here. So that's your IA. And to make it look nice, you just join up the parallel pieces. Nice. So that's the first one. So number two, the other one is IB. All right, so let's go back to the diagram. Derive. So we have IBC. So IBC minus IAB. And as like I showed you, you can just write this in the opposite direction to make it easier to see. You don't have to, but I just like to do that. It's easier to see for me. So IBA would just be the inverse of this. All right, so that will be, so this is IAB. So IBA would just be right here. Just draw the parallel to it right here. Right, and you just like we did before, you just connect the two from the center. So this here connecting to this point here. So just draw the line. And you have your IB line. Yeah, and we just draw you connect the other pieces to make it look nice, right? Yeah, so make it look like a normal field, right? And the last one is, yeah, I will draw it up here because of space. Yeah, IC. So IC would just equal to your ICA plus your ICB. That's right, and it's another way that easier for me to plot one time, right? So ICB would just be the flip of this piece here. So just draw that going up like this, not too long. Connect the other parallel piece to it. Right? So no matter which side they start with first, right? They both gonna be parallel to each other. It really matter, right? And you just connect the two. So you know this here gonna connect from this here, draw it up. So you have your IC, right? And to make it look nice, you just connect all your parallel pieces to it. So this will connect to here. Just like that, finish. That is it. Phasor, finish. That is it. Right? So the same relationship that we're showing you is from here, then to here is 30 degrees. That's what the relationship they're trying to show you. It's the same relationship for the star and the delta. It's just for the star that's on top. So I'm gonna show you. For the star, the 30 degrees was on top, so it was up here. Right? So you're saying that the phase and the line is opposite. So therefore, your line leading the phase. Yeah. Because if they also do a race, this will win. He will be behind. Right? And then for the delta is the opposite, it underneath. Yeah. So IAB will win in a race because IA behind. Yeah. So that's how others know what leading and lagging. Like if I just spot point here and I say on the mark, guess I go, obviously IAB will win because it's already in front. So IA lagging and IAB leading. So we'll just go in that direction. Right? Don't need to overcomplicate it. Right? And those are your phasors. Right? All right, so the last thing is which is the easiest thing is your power equations. I was going to tell you, the power equation is the same whether you're in the star or the delta for a balanced system. Keyword being for a balanced system, right? So in a three-phase system, the total power transferred is the sum of each phase, right? So that is where they get the three, well, by phase, by the power of one phase, right? But because once this is a balance, right? The power, this is the base equation, right? With respect to a phase. So if they were to give you V phase and I phase, you could get the power, yeah? And then the equation with respect to a line is this, yeah? It's the same for both configurations. So once you remember it, you're not gonna forget. Theta is the angle between your phase voltage and a phase current. Something like a power factor from 1000. Yeah? So that's what theta is. So like if you have, there's your phase voltage, trying to say phase current, sorry. Yeah, so if I give you a phase voltage are like 30 degrees and a phase current is like 10, your theta will just be the theta will be minus a theta. Yeah? It's just the angle between your phase voltage and your phase current. So you learn something. All right, so these are your two equations for power. All right, first one is just 3 by the P phase, which is just power is equal to VI. So that'll be V phase by I phase. So if they give you V phase and I phase and they give you the power factor, yeah, you could find the power. Yeah. Or if they give you the V line and the I line, if you get the total power. Right? These equations are linked. Right? Remember, whatever they give you the configuration, whether they say star, you know for star, the I line is the I phase. So if they give you the phase, you automatically have the line. If they say delta, the phase voltage is equal to the phase voltage is equal to the line voltage. So if we give it the line voltage, to automatically give it the phase voltage. So that's something to keep in mind, and it could work these equations depending on what values they give you. All right? And with that said, that's all I wanted to go through. So I'll show you the equations for power, 3V phase, I phase, cos theta, and or root 3V line, I line, cos theta. I'll show you how to plot the phasors for the star and the delta. I'll show you the equations. I'll show you the relationship with the direction. Um, right, I'll show you the graphs for them, the phase and the lines. And I went through this with you already. I'll show you this and that is all I wanted to do. So next week, I'll go through some of the questions with these. It will be past paper questions, right? And during this week, I'll send some questions in a PDF in the group chat, so y'all could go through it, right? So I'll stop and I'll stop the record, right? You all have any questions? So I'm going to go over